Okay, this is my first attempt with doing a video key. Um, if you saw the setup for this, you might find it comical. So if you hear some shuffling around and bumps and scratching, that's me trying to move this apparatus that I've created to hold my camera above our worksheet here. It'd help if I'm on the right side to start with, maybe, perhaps. Here we go. All right, so let's start with 1A. This is all really easy stuff. It's just conceptual, but get the concepts down real sound before you move on, so before we start putting numbers to this. So just go through it. It says in a solution or in a situation shown below, a spring. So we want to kind of understand it's a spring launches a roller coaster cart from rest. It's another big deal on a frictionless track into a vertical loop. So it says assume the system, right? We're always concerned about the system, especially now that we're dealing with energy, because we look at like energies in terms of the system and where is that energy going? Is it staying within the system? Is it leaving? Is it out? Or is it coming in? Is it when? And how we define the system really dictates whether we're having transfer into the system or around the system. So here we have a system consisting of the cart, earth, the track, and the spring. All right, so we'll go in there and say, well, this is going to be cart. Put an E for earth, track, spring. All right, so we got everything down there. Now, what I've been doing is I've been writing all of my forms of energy across the bottom, even though some of them are not present. But I always start with elastic, EEL, kinetic, and gravitational. Right? And I'll go ahead and I'll do the same on the other side. So we have EEL, EK, and EG. All right, so what do we have here? Well, in this first spot, we're at rest. So that means that we have no EK. What we should really do here is do we have gravitational energy? Well, in this situation, we're going to call the road height 0 meters. See that over there, kind of off to the side. Maybe I'll draw it right here as well. And so we have height equals 0 meters. There you go. Okay, so with that being said, our car is at our 0 meter mark. So we also have no energy gravitational. And then EEL. Well, what does a spring possess in terms of energy? Well, I don't really know. But we can generalize and say that we'll have 4 units of energy. Elastic. All right. And then this cart gets going. I see some speed marks. Remember from chemistry, we had those whoosh marks on our particles. And it seems that we have some whoosh marks on our car. So they're moving. So do we have energy elastic anymore? So this is, if we're looking at this, is part A at rest. Part B is in motion all the way above within the loop. Well, we have no more energy elastic. There is no springs. Energy elastic is going to be like your springs, any kind of deformation. So deformation meaning like change in shape or something like that. And there's none of that, or at least none that we're aware of. Okay, kind of come over here. And we said we have those whooshies, right? So we have energy kinetic for sure. Some energy kinetic here. We'll just say that there's 2 bars of energy kinetic. Not that I'm set on that. If you said 1 bar, that would be fine. Remember, this is just conceptual. So it's really saying, do I have energy kinetic? And say, yeah, I got energy kinetic, those whooshy marks. And then gravity. Well, am I above 0 meters. Yeah, absolutely. We've climbed quite a bit, and that is where our 2 bars of gravitational energy is coming from. Now, something that I want to note is that the moment, so somewhere between A and B, the moment that this spring let loose in this car was at 0 height still, all of that spring energy was kinetic energy. So if we had taken a snapshot around here, we would have had all kinetic energy. But as it climbed that loop, it took away from the speed, right? Think about if you went skateboarding or something, or roller skating, or just running. As you approach that hill, it takes away from your energy. It takes away from your speed, especially if you're coasting, and there's no more input. So yeah, we took away that kinetic energy. It's going, right? We're losing a bar here, and then all that energy isn't, I shouldn't say losing, because what we're doing is actually transforming it, right? So as we drop kinetic energy, we gain gravitational. All right? And then our equation, our conservation of energy equation, is going to be something like this. We're just going to list EEL equals EK plus EG. And right now there's no numbers here, but something that I do want to make a note of is as we get closer to plugging stuff in, well, we know EG, what actually that means, and that's actually mass times gravity times height, right? So if we didn't know what exactly EG was, but we knew the mass and the height, and we knew what planet it was on, we knew its gravity, then we can actually figure out a lot about this. All right, moving on. Boy, I am not doing well on time here, people. This is gonna take some getting used to here. Okay, it says for this one, repeat problem 1A for a frictionless system. Include the cart, earth, track, but not the spring. Okay, so the spring is not part of our system. So let's go. Let's say cart, earth, track. Right, and we're gonna write out our same stuff. EEL, EK. EG, same over here, EEL, EK, EG. Okay, and then I'm going to say, well, there is no spring in this system. Okay, but the spring is still there's still energy there, right? There's still energy stored in that spring. And when it lets loose, it's still going to affect the cart. And the cart is part of our system. Well, we don't have any elastic energy. We've got to label height. Height equals 0 meters. All right? So there is no gravitational energy. We're still on the ground. We're still at height equals 0. And as far as I can tell, this car is not moving just yet. So we have no energy kinetic. And again, we'll call this A. We'll call this B. This is A. This is B. Well, over here, the cart has speed and it has gravity. So let's go back and let's apply the same amounts of energy as we did in part A of this question. So we got 2 gravitational and 2 kinetic. All right, where did the energy come from? Energy isn't just made, but it certainly didn't come from within our system. So here we have to consider that the energy came from outside the system. So we have what we call win, or work in. And work in is going to be by spring and in the amount of 4 bars of energy. And that's where our 4 bars of energy come from. All right, so we're going to have win. Now here we're going to have, our equation is going to be a little bit different. We're going to say work in equals EK plus EG. And that's about it. And we're typically going to be given this when it is talked about. We're going to say, well, work in is going to be 83 joules, and going to have, again, we'll know that gravitational energy equation, and we're probably going to know kinetic at some point in our life too. So these are going to be solvable, just not right now. We're still in that conceptual land, but I do want you to keep in mind that these are solvable. So here we have a little bit of a different problem. Actually, it's the same problem, but there's something very important here. It says assume that there is friction between the cart and the track. Okay, there's two ways that I want to address this. So again, I'm going to come back here and I'm going to say, oh, we have EL, we have K, energy gravitational, EL, K, G, height equals 0 meters. And then problem 1A said we have the cart, we have earth, we have the track, and we have spring. Okay. Now, this bothers me about this question. It says there is friction between the cart and the track. All right, so one would imagine that we're going to have wout, and I would agree with you. Right, so let's set this up to have that same 4 bars of elastic energy, right? And we're going to say it's gotten to the same height as all of these problems. So our EG, for the sake of staying standard, we're going to say that's still 2 bars. And then we lost some energy to friction. We'll say we lost 1 bar energy, so that came from our kinetic energy. Now, this bothers me. The track is in my system. So really, the cart gave the track energy. And who knows what that energy is going to be in. Maybe he's deforming the track. If we've ever seen Hot Wheels go around in a loop-de-loop, like that track kind of gets oblonged or something like that. So maybe there is some sort of deformation of the track, and we have some elastic energy because of that. But we say it's from friction, and we don't have energy thermal. So what I guess we're led to believe is that we have wout, and that is work out, right? Wout. And this is by friction. And then the amount of 1 brick. Now, again, what I don't like about this is that it really didn't go out of our system. It didn't really wout. It wasn't out. It was just within. So it was still work, but it was work within our system. And we don't really talk about that too much. So I guess the best way I can explain this is that there is wout by friction. And really what we should do is not consider the track as our part of our system. But that's just me. Maybe somebody else will tell you different. So in this situation, we have EL minus work out equals EK plus EG. And again, we're going to get a little less conceptual as time goes on. So make sure you take that into consideration. Oh yeah, we're at 13 minutes. This is terrible. Pellegrini, step up your game. All right, so here we have the same exact problem from A, except look, our position changed. Okay, cool. So let's just fire these in here, write down our energy, EL, EK, EG. System is cart, track, spring, and earth. EL, EK, EG. And let's say we get the 4 bars going on. Lovely, great. And then here we're going to have some kinetic energy. And now notice that our car hasn't gone up all the way. So it hasn't got that 2 bars. Maybe we're at just like 1 bar here, right? So we have 1 bar of gravitational energy. Well, we had 4 bars of elastic, so where does that other one go? Well, it's traveling faster at that time, right? And we talked about that in the first question. If we had taken that snapshot in a little different spot, like here, it would have been all kinetic. but here we're starting to go up, so we're dropping a little bit of kinetic, cashing it in for some gravitational, but not as much as we did when we were up here, where we cashed in a lot of kinetic energy for gravitational. So here is going to be EL equals EK plus EG. Pretty simple stuff. Moving on. Car rolls up a hill until it stops. Right, so we have no kinetic energy at the end. Do this problem for a system that consists of the car, the road, and the earth. Car, road, earth. Again, go quick with this. Don't want to take up any more of your time. Okay. And it says here, assume that the engine is turned off. So it looks like it's just coasting to a stop. It's in neutral. There is no friction. So we have just straight up kinetic energy. And I don't know if 4 is the right number, but I like doing 4. And then it comes to a stop. So all that 4 turns into gravitational energy. Right, and here EK equals EG. Here we have friction, so we have wout. So we have car, road, earth. We have wout, or work out by friction. And in the amount of 1 brick, I'm just making that up. Doesn't matter. Just make it reasonable. Here we're going to start with those same 4 bars. I try to keep it as constant as I can. So EK, and we're going to get 3 bars of EG because one of them went to wout. So we have EK minus wout equals EG. Okay. Here, let's see here. What do we got going on? It says a person pushes the car up with the parking brake on. Assume that the system includes the car, the road, the earth, but does not include the person. So here we have car, road, earth. Kind of scribbled that out right there. I didn't mean to put us in the middle of writing person there. EL, K, G, and here we're going to have, assuming some frictional loss because we have the brake on. So we get to say, well, there's wind here, and this is by person. Let's call that in the amount of 4 bricks of energy. And we're going to have wout by friction. And call that in terms of 1 brick of energy. And then we're going to have EG. Right, so we get 3 of EG. So here we have 1 minus wout equals EG. Okay? All right, and then our last one. Almost last one. 2 more. Repeat 3A, and this one includes the person. So we have, let's see here, car, road, person, earth, put in all my, I don't know if I'll have you guys continue this trend, but other teachers are doing it, so feel like sticking with the program there is probably the best. So here we go. This is including the person, so the person is providing that kinetic energy. That car is moving. And 3A, I believe, we are talking about friction, so we're going to have a little bit of work out by friction. We'll call that 1 bar. And then I think, what did we give? EG. EK is 4 bars, I'm sorry. And then energy gravitational will be 3. And then here we're going to have EK minus wout equals EG. Last one. Loaded bricks rest tightly on a coiled spring and then is launched into the air. Assume the system includes the spring, the brick, the earth. No friction. So spring, brick, earth. Now, what do we got going on? Well, we have a boatload of elastic energy pent up in that spring. And that elastic energy is, we got some whoosh lines, so we're moving. So we're going to say that we got 2 kinetic, and then we've come off of height equals 0 meters, which I have been forgetting to put down. So don't do what I'm doing. EL equals EK plus EG. All right, cool. That's it. That's all I got for you guys. Took a while. Hopefully it'll be quicker next time. Browse through what you need. I'm going to have you probably make corrections to your paper and then submit it on Canvas. So we'll see what happens. Have a great night. Goodbye.